All right, today we're talking about something pretty amazing. A group of molecules that are basically the secret architects behind some of the most important and beautiful things in nature. We're talking about coordination compounds. Okay, so let me ask you a question. What do you think connects the deep red of your blood, the green in a plant's leaf, and, say, a sparkling ruby? I mean, on the surface, they seem like they have absolutely nothing in common, right? Well, it turns out they all share this one incredible chemical secret. And that secret link, it all comes down to a very specific kind of chemical structure. You've got a central metal atom and it's surrounded by a bunch of other molecules. These things are the absolute powerhouses behind so many processes we see every single day, from the oxygen our blood carries to the sunlight that plants use for energy. So that secret ingredient is a coordination compound. Check this out. Hemoglobin in your blood, that's a coordination compound built around iron. Chlorophyll, which makes plants green, that's built around magnesium. Even vitamin B12 has cobalt at its core. And that stunning color of a ruby? Yep, that's thanks to some chromium ions hanging out inside a crystal, forming, you guessed it, a coordination compound. Okay, so how on earth did we figure all this stuff out? Because it was definitely not obvious. To get the full story, we have to travel back in time, back to the late 1800s, and meet the brilliant chemist who basically cracked the whole case. That chemist was Alfred Werner, a Swiss scientist who came up with this totally revolutionary theory. I mean, it completely flipped how we thought about chemical bonding. His work basically laid the entire foundation for everything we know today. And yeah, it was so groundbreaking, he nabbed the Nobel Prize for it in 1913. So, what was the big puzzle that Werner was so obsessed with? Well, it was all about these cobalt compounds. See, they all had the same basic formula, cobalt chloride and ammonia, but they looked different. They had different colors, and they acted differently when you dissolved them. How is that possible? It's kind of like having the exact same set of Lego bricks, but depending on how you click them together, you get totally different models. That was the mystery he just had to solve. And here's how he started to piece it together. He ran this experiment where he added silver nitrate to his solutions. Now, silver nitrate reacts with any free-floating chloride ions and makes this solid stuff, a precipitate. What he found was amazing. The yellow compound, it dropped all 3 of its chlorides. But the purple one only let go of 2. And the green and violet ones, they only gave up 1. This was a huge clue. It told him that some of the chloride atoms were stuck really tight to the cobalt, while others were just hanging around. So Werner had this brilliant idea. He proposed that metals don't just have one way of bonding, but 2. He called them valences. The primary valence is the one we're kind of used to. It's the ionic charge, and it's balanced out by ions like those free chlorides. But then he said there's a secondary valence. This is a totally different type of bond. It's strong, it's directional, and it holds a specific number of molecules directly to the metal. And that was the breakthrough that explained everything. Werner's theory really set the stage for how we understand these things today. So let's break down the anatomy of a coordination compound piece by piece. Right at the heart of every single one of these compounds is a central metal atom or ion. It's the core, the main hub that everything else connects to. You can kind of think of it like the sun in a solar system. And the things that attach to that central hub, we call them ligands. These are the molecules or ions that bond right to the metal. Now, some ligands are simple. They're called unidentate, and they just grab on in one place. But others, called didentate, can grab on in 2 spots. This creates a way more stable structure, something we call the chelate effect. It's kind of like trying to grab something with one finger versus using your whole hand, or even better, like a crab grabbing onto something with both of its claws. That's a seriously strong grip. So when you take that central atom and all the ligands attached to it, that whole package is called the coordination sphere. And you'll see it written inside square brackets in formulas. That's our way of saying, hey, this whole thing acts like one single unit. This is the core functional part that gives the compound all its cool, unique properties. Okay, now for one of my favorite parts, and probably the most obvious feature of these compounds, their amazing, vibrant colors. And this isn't just some random fluke of chemistry. The color is a direct result of how their electrons are set up. So, why? Why are so many of them so brightly colored? Well, the answer is all about how their electrons play with light, and we can explain it with a really elegant model called crystal field theory. Okay, stick with me here. If you have a metal ion just floating by itself, its special electron orbitals, the d orbitals, all have the same energy level. They're all on an even playing field. But when the ligands come in to form bonds, their electrons start to push back on the metal's d orbitals. And this push isn't even. Some of the d orbitals get pushed on a lot more than others, and this forces them to split into two different energy levels, a low energy group and a high energy group. And that energy gap, that split, is the key to color. Here's what happens. White light, which has all the colors of the rainbow in it, shines on the compound. An electron in one of the lower energy d orbitals sees that light and gets excited. It absorbs just the right amount of energy from one specific color of that light to make a leap up to the higher energy level. So what happens to the rest of the light? The light that wasn't absorbed gets reflected, and that's the color that hits our eyes. So for example, take this titanium complex here. It's really good at absorbing light in the blue-green range. Since it basically eats the blue-green light, what's left over to bounce back to our eyes is its opposite, its complementary color, which is a beautiful violet. So the color we see is literally the color of light that the compound rejected. And this is where it all comes together. Understanding this stuff isn't just a cool science experiment. These compounds with their unique structures and properties are absolutely essential in so many different fields. It's all about their ability to hold a metal ion in a very specific, very precise way. That makes them perfect for all sorts of special jobs. Think back to hemoglobin. It holds onto that iron ion just right so that it can grab onto oxygen in your lungs and carry it all around your body. And seriously, the applications are just everywhere. We use them in mining to pull gold right out of ore. They're used to make super pure nickel. They're powerhouse catalysts in the chemical industry. In medicine, a platinum compound called cisplatin is a major anti-cancer drug. And another one, EDTA, is used to treat lead poisoning because it's so good at grabbing onto those toxic lead ions and helping your body get rid of them. The list just goes on and on. You know, one of the sources for this explainer said it perfectly. Coordination compounds are the backbone of modern inorganic and bioinorganic chemistry and chemical industry. I love that. They're not some obscure little topic in a textbook. They are fundamentally a part of how our world works, from our own bodies to massive industrial plants. So yeah, from the sparkle of a gemstone to the battle against cancer, these small but mighty chemical structures are right there in the middle of it all. And it really makes you wonder, doesn't it? With how versatile they are, what problem are these tiny chemical architects going to solve for us next?